I'm going to explain how to do the problem at the top of this page. And so the reason that I'm doing it is a lot of people have emailed me questions. And so to take you through this problem, I'm going to say that at first this ball is at rest. That's important in this problem. In order for the ball to be at rest, that means that acceleration is 0 and we are in equilibrium. Equilibrium means that our forces in the x direction are going to cancel, so the left forces have to equal the right forces, and the y direction forces have to cancel, so the up forces have to equal the down. When we're doing any of these problems, of course, we're going to start off by drawing a nice force diagram. So for this force diagram, you'll see that there was this blue force of gravity drawn straight down, that we also had a force of tension 1 in the direction of the rope, and the force of tension 2 also in the direction of the rope. Remember, the length of the rope does not tell us how long to make the force of tension. Only the direction of the rope shows us what direction to make that force of tension. Once we've drawn our force diagram, forces at angles will be split up into components. So when I'm splitting up the force of tension 1 into components, it has this horizontal component that's pointing to the left and this vertical component that's pointing up. And then when I'm looking at force of tension 2, force of tension 2 has force of tension 2 in the x direction. So there's that horizontal component, and then the y direction, which is that vertical component. Once I've drawn these components, then I can start looking at these equations and say, in order to maintain equilibrium, any force that is pointing directly to the left must be balanced out by a force pointing exactly to the right. So my force of tension 1x and my force of tension 2x must cancel each other out. They are the only forces acting left and right. They must be equal to each other. They must pull with the same amount of force in order to maintain equilibrium. Now in the y direction, I have two upward forces. I have both the force of tension 1y and the force of tension 2y. And those two added together have to equal the weight. Both of them together are supporting the weight of the object. These two forces do not have to be equal to each other. In fact, those two forces are only equal to each other if the angle of the string is the same. We can see when we zoom in on this picture that these two angles are not the same, which means our y components will not be the same. They just have to add up to equal the force of gravity going down. If string 1 was all the way vertical, it would be supporting all of the weight of the object. If string 2 was all the way horizontal, it would be supporting none of the weight of the object. Together, they're both supporting a little bit of the weight of the object. And it turns out that the more vertical the string is, the more of the force of gravity it is holding. And so if you have two strings at unequal angles, you must make their x components the same size. And from where their x component ends, that's where you draw the y component up. From where this x component ends, that's where I draw that y component up. And then I can go ahead and put in my hypotenuse of my right triangle as that force of tension. So I first drew the horizontal legs actually to scale. Then I drew the vertical legs, and then I used those together to make the hypotenuse of the right triangle. So the x components had to balance, the y components had to add up to the force of gravity. But the more vertical the string is, the larger the force of tension y is. The more horizontal the string is, the smaller the force of tension y is, because these x components have to be the same size. For the second part, when it's in an elevator but at a constant speed, because it still has an acceleration of 0, we still have to maintain equilibrium. And so all of those forces would still maintain the same size.